Pluto is a distant and confounding minor planet that was once part of our planet group's planetary family. Anyway, current alarming announcements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with an amazing divulgence. They suggested that this chill world is on an impact course with Neptune. Yet how, if this occurs, and what might be the results of such a significant event? Are we seeing an intriguing cosmic eccentricity, or something else entirely? To this approaching limitless effect, join us as we investigate the conceivable outcomes of a Pluto-Neptune influence. Pluto, a past planet that was downsized to a dwarf planet, is somewhat due to its odd orbit, and it stays a subject of interest and study in the grandiose community. As indicated by late expectations by leading specialists, Pluto's direction is dangerously close to Neptune's. Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a possible dangerous accident between these two planets, which represents a critical risk to Earth. How are such occurrences even possible? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It requires an unbelievable 248 years to complete a single orbit, which means that since its discovery in 1930, not even completed one full revolution yet. However, the interest doesn't stop there. Pluto's orbit is marked by its astonishingly curved shape that deviates altogether from the almost round orbits of the major planets. What makes Pluto's orbit even more astonishing is its inclination. Of 17 to the ecliptic plane, course Pluto follows is much steeper compared to other planets. One of the most interesting parts of Pluto's orbit is its crossing point with Neptune's. For approximately 20 years in each orbit, Pluto actually draws closer to the Sun rather than Neptune, challenging our previous expectations from their positions in the planetary system. This prompts the logical inquiry: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The investigation of Pluto's orbit began shortly after its discovery. Initially, astronomers attempted to determine its unique orbit. Unlike other planets whose orbits are typically located close to the ecliptic plane, Pluto's orbit stood out with its steep inclination and curved shape. The mystery deepened with the realization that Pluto's orbit does indeed cross Neptune's. The stability of Pluto's orbit amidst these complexities is evidence of the intricate nature of celestial mechanics. The three-body problem in space focuses on determining how three bodies, similar to Pluto, Neptune, and the Sun, move and affect each other through their gravity. Pluto's orbit is, in fact, turbulent. Minor starting condition deviations can lead to significant differences over millions of years. However, these unusual properties of Pluto's orbit have been found to maintain stability over especially long timescales, keeping tumult under control. Recent simulations have helped us understand how the giant planets, like Neptune, Jupiter, and Saturn, influence Pluto's orbit around the Sun. Jupiter's massive gravity is strong enough to keep Pluto on a stable path, possibly for billions of years. These quirks are essential in maintaining the celestial order and consistency dynamics. Without these factors, our local planetary system would serve as a location of much more unrest and unpredictability. Pluto's orbit is a remarkable illustration of the mechanics of the heavens at play, displaying both stability and chaos within our local planetary system. The unique characteristics of its orbit, influenced by the gravitational forces of planets nearby, particularly Neptune, highlight the intricate and dynamic nature of space. Predicting major events, particularly when it involves turbulent Pluto's orbit, presents tremendous challenges. The inherent unpredictability of these systems means that long-term forecasts are often filled with uncertainty. During computer simulations, they offer a powerful means for understanding and predicting the future behavior of celestial bodies. They also highlight the limitations in our ability to predict. So why are prominent astrophysicists only now raising concerns about a potential crash between Pluto and Neptune? Despite the numerous complex forces working to prevent such an event, Neil deGrasse Tyson and Michio Kaku, both renowned figures in astronomy, have expressed concern about a possible collision between Neptune and Pluto. If Pluto and Neptune were to collide, it would be a captivating and devastating event in our neighborhood planetary system. The impact would release an immense amount of energy, probably breaking Pluto, given its smaller size and icy composition. Debris from the collision could scatter across the planetary system, potentially posing danger to other planets and their moons. For Neptune, such a collision could alter its current atmosphere and possibly its orbit, depending on the specifics of the crash. Michio Kaku, a well-known theoretical physicist known for his work in string theory, brings a unique perspective to the discussion as well. His views on the future of space exploration and the connection between celestial mechanics and theoretical physics offer valuable insights into the mysteries of major phenomena like Pluto's orbit. Comprehending the intricate gravitational orbital elements and interactions of celestial bodies like Pluto can yield important information for the future of space missions. This knowledge can help in navigating the planetary system more efficiently, predicting potential hazards, and even planning missions to the outer reaches of our solar system and beyond. The lessons learned from studying Pluto's orbit can be applied to exploring other celestial bodies, providing a roadmap for how we might approach and understand distant worlds. Regarding the physics of planets, theoretical mechanics, and celestial mechanics, physics are deeply interconnected. The movements and interactions of planets, including the gravitational dance between Pluto and Neptune, relate to the fundamental principles of physics. If Pluto and Neptune were to collide, it would be a monumental event in astronomy. It's offering a unique observational opportunity that could potentially connect with string theory. String theory, theoretical framework in which the point-like particles of particle physics are replaced by strings with no dimensions, aims to explain the fundamental forces and matter in the universe. The collision could create extreme conditions of energy and gravity, possibly creating circumstances where predictions made by string theory could become detectable. For example, the high-energy impact could provide insights into the behavior of fundamental particles and forces. Under extreme conditions, a key area of interest in string theory, while the direct effect on Earth would be negligible due to our distance from the outer planetary system, the scientific implications of such an event could be profound, potentially contributing to our understanding of the fundamental nature of the universe as described by string theory and other areas of theoretical physics. Pluto's confounding dance around the Sun continues to enrapture scientists and enthusiasts alike, offering a window into the complexities of celestial mechanics. While its reclassification as a dwarf planet sparked discussion and redefined our understanding of planetary bodies, recent discoveries about its orbit have reignited interest in its role within the local planetary system. Neil deGrasse Tyson and Michio Kaku, two distinguished voices in astronomy, have raised concerns about a potential crash between Pluto and Neptune. Shedding light on the complex dynamics at play in our cosmic neighborhood, their warnings emphasize the importance of understanding the gravitational interactions and orbital mechanics that govern celestial bodies' movements. Pluto's orbit, characterized by its unpredictability and steep inclination, defies traditional assumptions and challenges our view of planetary motion. Unlike the nearly circular orbits of its neighboring planets, Pluto's path follows a unique course, intersecting with Neptune's orbit at various points throughout its long journey around the Sun. The gravitational influence of other planets, particularly Neptune, plays a crucial role in shaping Pluto's orbit and maintaining its stability over hundreds of years. In spite of the tumultuous nature of its path, numerical simulations and theoretical models play a vital role in predicting the future behaviors of celestial bodies and understanding the complex interactions between planets. These simulations show that while Pluto's orbit is turbulent over thousands of years, it remains relatively stable within the broader framework of the solar system's gravitational field. The potential for a collision between Pluto and Neptune, as proposed by astrophysicists Neil deGrasse Tyson and Michio Kaku, lights the ongoing uncertainties and intricacies in planetary dynamics. While such an event remains hypothetical and highly unlikely in the near term, the gravitational dance between Pluto and Neptune underscores the fragile balance of forces that governs celestial bodies within our solar system. Beyond its scientific significance, Pluto's study offers practical insights for future space exploration missions. The New Horizons spacecraft, launched by NASA in 2006, provided exceptional images and data of Pluto and its moons during its historic flyby in 2015. The mission revealed stunning details of Pluto's surface features, including mountains of water, ice, and vast fields of frozen nitrogen, enhancing our understanding of the geological processes shaping the distant dwarf planet. The success of the New Horizons mission highlighted the technological advancements and collaboration necessary for deep space exploration. By studying Pluto and its moons, scientists gained valuable insights into the diversity of celestial bodies and the environmental conditions present in the outer regions of the solar system. These discoveries have implications for future missions to explore other dwarf planets and trans-Neptunian objects. Furthering our understanding of planetary formation and evolution, Pluto's status as a dwarf planet has also sparked discussions about the criteria used to classify celestial bodies within the solar system. The debate over planetary classification reflects broader questions about scientific classification systems and the evolving nature of astronomical information. As Pluto meets some criteria for planetary status, such as orbiting the Sun and having sufficient mass for self-gravity, its classification as a dwarf planet highlights the diversity of celestial bodies beyond the traditional 8 planets. Studying Pluto's orbit expands our knowledge of celestial mechanics and planetary dynamics to the outer reaches of the solar system. By examining the interactions between Pluto, Neptune, and other celestial bodies, scientists can gain further insights into the formation and evolution of planetary systems. These insights are crucial for developing theories about the origins of our solar system and understanding the processes that shape planetary bodies over billions of years. Pluto's discovery and subsequent study have contributed to our understanding of planetary migration and the formation of the Kuiper Belt, a region beyond Neptune populated by small, icy bodies. Studying Pluto's orbit provides clues about the gravitational interactions that may have influenced the formation of planets during the early stages of the solar system's evolution. Understanding the complexities of the universe's mechanics can also provide guidance for future missions of space exploration, including the search for habitable worlds beyond our solar system. By studying the motions of distant celestial bodies, astronomers can identify potential targets for future exploration and assess the feasibility of traveling to other star systems. The potential impact of a Pluto-Neptune collision, while highly unlikely, serves as a reminder of the dynamic nature of the universe and the unpredictability of cosmic events. As we continue to explore the outer reaches of the solar system and beyond, the study of planetary orbits and celestial mechanics will remain a central focus for astronomers and space agencies alike. Pluto's orbit, which deviates significantly from the idealized paths of other planets, offers important lessons about the difficulties of planetary motion. The stability of its orbit over long time periods, despite its eccentricity, provides important insights into the balance of forces that govern the movements of celestial bodies. In a sense, the ongoing study of Pluto's orbit and potential interactions with Neptune reflects the broader challenges of understanding the universe at large. With each new discovery and each theoretical model, we continue to refine our knowledge of the cosmos, uncovering the mysteries of distant worlds.